Hello students, welcome you all. In mass spectrometry, today I will explain the types of peak in mass spectrum. In my previous lecture, I gave you the introduction of mass spectrometry, then the instrumentation part, and various ionization techniques like electron impact technique, then chemical ionization technique, and desorption technique like field desorption technique, fast atom bombardment technique, and so on. Now here I will discuss the various types of peak in any mass spectrum. So if you will see the mass spectrum, then which is drawn between relative abundance and m by z value, that is percentage relative abundance, and m by z value. Now in this mass spectrum you may see the various peaks. Suppose this is one of the peak which can appear like this, and the peak like this. These are the various peaks. So many peaks you may see in this way. This is the suppose many peaks which may appear. Suppose this is the mass spectrum. Now in this mass spectrum there are various peaks, and we can categorize the various peaks. Like suppose one of the important peak is the molecular ion peak. And which is also called as this parent ion peak. So molecular ion peak or parent ion peak. Now if you will see in this mass spectrum, this molecular ion peak that would be present at the extreme right corner. So, and we represent this molecular ion peak as like this, means radical cation. This is represented in the form of radical cation. So this peak, which is at the extreme right corner of this mass spectrum, this is our molecular ion peak. Okay, so we can write it is present at extreme right corner in any mass spectrum. Now, so if you will see, I have drawn some more small peaks at the extreme right corner. So these peaks are the very small peak in comparison to this peak. So these peaks I will discuss, which is in later. That is, these peaks are the isotopic peak. So they are no doubt they are at the extreme right corner, but we take this peak which has the higher intensity in comparison to this peak. This is taken as the molecular ion peak. So here we can say except isotopic peaks. So these small peaks which you may see, these are the isotopic peaks. So except isotopic peak, now, if you will see, then this peak has the m by z value. If you see, this has the highest m by z value. So it has highest m by z value. And if you will compare this molecular ion peak with the molecule, okay, if we compare this with the molecule, then between this molecule and molecular ion, if we remove one electron from the molecule, then we get the molecular ion peak. So how we get it? Suppose if we have any molecule, gaseous molecule, and this gaseous molecule, first of all, this any sample is vaporized, and this vaporized sample is then ionized in the ionization chamber, and further fragmentation of this molecular ion takes place. So this molecule, in presence, if it is bombarded with an energetic beam of electron, then it would be one of the electron from this molecular ion that would be removed, and after removal of one of the electron we get the radical cation, and this is called as the molecular ion peak, and two electrons are also removed. So one of the electron is removed from this molecule and another electron is reflected. These are the reflected electron, so two electrons. Okay, so this is the molecular ion. This is the molecular ion which show the peak here. So if you will compare these two, then the molecular mass of a molecular ion and the molecule is same. So if we remove one electron from any atom, then what will happen? The molecular mass will remain same. So as you know, the molecular mass, it depends upon the mass of proton and neutron. It doesn't depend upon the mass of electron, as the electron has the very negligible mass in comparison to the proton and neutron. So this molecular mass of this molecular ion is same as that of the molecule. So the molecular mass, we can write the molecular mass of molecular ion is same as molecule. Okay, now next important point for here, that this about the stability. What about this intensity of this molecular ion? So the intensity may be very less, it may be highly intense. Sometimes it is so much intense, it may go over here. It may be highest intensity, highest relative abundance. So the intensity of this molecular ion peak, the relative, or we can say the relative abundance of this molecular ion peak, it depends upon the stability. Okay, it depends upon its stability in mass analyzer. So what we can write, the intensity or the percentage relative abundance of molecular ion peak is directly proportional to its stability. So if it's stable, then it will go into the mass analyzer. If it is not stable, then it will undergo fragmentation. Okay, so various molecule has its various stability. It depends. The stability depends upon the type of the molecule. Now, suppose if we compare, suppose if we have the alcohol. Okay, if we have an alcohol and suppose aromatic compound. If I have alcohol and aromatic compound, aliphatic alcohol and some aromatic compound, then which is more intense, which will give more intense molecular ion peak? So no doubt aromatic compound will give the more intense peak. Why? Because aromatic compound, that is stabilized by the resonance, and it could not be fragmented further in the mass analyzer. So that's why, and we know that also this aliphatic alcohol undergoes dehydration. Okay, so if we compare, suppose if we have aromatic compound, then it will show very intense peak. Similarly, some of the stable compound, aromatic compounds, or some unbranched hydrocarbon, and then suppose if we have some conjugated compounds, we may have the conjugated compounds, suppose, because you know that conjugated compounds are also resonance stabilized. So aromatic compound, then conjugated compound, unbranched hydrocarbon, and then we have the various ketones, esters, and so on, like this. So we will discuss more about this later on. So esters, and then suppose if we have any branched hydrocarbon, then branched hydrocarbon can easily be fragmented in comparison to the unbranched hydrocarbon, because branched hydrocarbon, that may give you the stable cation or stable radical, whereas unbranched hydrocarbon, it will not give you the as stable radical as the branched hydrocarbon. So then we may have suppose a branched hydrocarbon, and then we may have suppose alcohols. And you know, this alcohol, it undergo easily, dehydration of alcohol easily takes place. So that's why it means the molecular ion of this alcohol, it will undergo fragmentation very easily, and that's why it is less stable, and as it is less stable, that's why it will not show the intense molecular ion peak. So very weak molecular ion peak due to this. Weak, again it's quite weak. So this is very weak, then this is weak, and this is intense, and so on. So this is about the molecular ion peak. Next type of peak that we may see in mass spectrum, that is, we may call it as a base peak. Now in this mass spectrum, which is the base peak? So the peak which has the highest intensity, highest relative abundance, that is the base peak in any mass spectrum. So this peak is the base peak. This peak is your base peak. Okay, so peak having the highest intensity. It has highest intensity, or we may say, or percentage relative abundance. Relative abundance, we say relative abundance. Why relative abundance? Due to this base peak, because the relative abundance of this base peak is taken as 100, and the relative abundance of all other peaks are calculated relative to this base peak. So that's why we name it as a relative abundance here. That's it, relative abundance. So its abundance is arbitrarily taken as 100. Taken as 100. And third one, the relative abundance of all other peaks are calculated, or the abundance of all other peaks are calculated relative to these peaks. So abundance of other peak are calculated relative to this base peak. So this is the importance, this is the main significance of this base peak, that abundance of other peak is calculated in comparison to this base peak. That's why it is called as the base peak. Now next peak, that is the next peak is the metastable peak. Now let us see the another type of peak, that is metastable peak. Metastable peak. Now here in this mass spectrum, if you will see, no other this metastable peak, I have not shown any metastable peak here, but if I want to show, and let us say this is the metastable peak here. This is the metastable peak, and this is quite different from this peak. We can easily recognize this metastable peak in comparison to this. Why? We can see that this metastable peak is quite broad, is quite diffused in comparison to this, where these are the sharp peak. So molecular ion peak, this is the base peak, or these are the fragments of this molecular ion. These peaks are the fragments of this molecular ion, whereas this is also a fragment, but it is in the form of metastable peak. Okay, so this is the peak which is broad, which is diffused is the metastable peak, and always this peak would be will have the very low intensity in comparison to the its peak from which it is formed. So one of the thing, it is broad and diffused and having very low intensity and having very low intensity. And how much low? About 10 to the power minus 2 times. Having very low intensity in comparison to we can say daughter ion, or we can say parent ion, daughter ion, like this, or we can say molecular ion, suppose. So this is the base peak, which is quite diffused in nature, which is quite broad in nature. And another characteristic of this peak, that this is it has you can say it is spread over the it is spread over some 5 and 10 this m by z value. And another thing that it has, if I find the position of this metastable peak, then it appears at a non-integer m by z value. So one of the important thing, it appears at non-integer m by z value. Means these peaks, if you see, then it may appear at, suppose some peak may appear at 80, some may at 43, some may at 29, some may at 15, but this peak will appear at non-integer value, means the position of this peak that will appear at, suppose, 43.3, 80.5 and like this. So this has position is non-integer. Okay, and it can easily be recognized by its shape. Okay, and if this peak is there, then it may interfere with some other peak also. Okay, so we may not get very resolved spectra if it is present. So resolution, in presence of this, the resolution of peak may become, resolution decreases. So that's why sometimes computer also removes this peak also. So this peak, the resolution of it can, so it can, this peak may decrease the resolution of spectra Okay, so that's why the computer may remove this peak also. So computer can remove this peak also. Remove this peak. Okay. Now, another thing, when it appears or where it appears, usually what I told you in instrumentation part, that such any molecular ion peak or this fragment ion peak, they are formed in ionization chamber. All peaks, they are formed in a ionization chamber. But this molecular ion peak is not formed in any ionization chamber. It is not it doesn't form in the ionization chamber, but somewhere in other field, which is called as the secondary region. So it is formed in a secondary region, and it may be in between, suppose, mass analyzer and this some electrostatic field, or we can say accelerating chamber. Okay, So it may appear, suppose this is the like this. So suppose various, this is the mass analyzer, this is mass analyzer suppose, and evaporation chamber, then ionization chamber, then we have this accelerating chamber, and then it is mass analyzer. So it will not appear, it will not form in this ionization chamber. So somewhere it may formed either here or either somewhere between this and this, and mass analyzer and accelerating chamber, and like this. So it is formed in secondary field region, we say. Okay, that is somewhere between accelerating chamber and mass analyzer. Okay, so these are some points for this metastable peak, and let us say some examples that how we can find the position of this metastable peak. So what I told you, this metastable peak, it appears at non-integer value, and the intensity is very low in comparison to its daughter or molecular ion. And suppose if we say we have a molecular ion, and this molecular ion, it is giving you the some this metastable ion. So suppose this is M1 and this is M2, and this is our metastable ion. This is metastable ion. Okay, this is suppose metastable ion, and now this position of this metastable ion, that is non-integer. So we can determine the position of this metastable ion peak is given by the formula M2 squared upon M1. This is the formula. Now suppose we have the para-aminoanisole. This is para-aminoanisole, and this gives you the further ion. It fragments, and suppose it fragments and one of the methyl radical is fragmented. It is fragmented from here. It is fragmented from here. So one of the radical would be here, another radical would be here, and this radical and this radical, it forms a bond over here, and finally what we get? We get this ion, metastable ion. This is the metastable ion which is formed like this. So this one and this one radical, this form double bond. Again here one of the double bond, and then again one of the double bond would be formed over here, and like this. So this is the, suppose here this m by z value for this is 123, and after if we subtract this one, that is 15 mass unit, if we subtract 15 mass unit, then this has the metastable, this has how much? 15. If we subtract it, then we have the 8, and we have 108. So 108 is the m by z value for this one, and further it may be fragmented, and suppose it is fragmented like this. Now if this is removed, carbon monoxide is removed, then we will get the 5-membered ring, and this has the mass number m by z. This is 80. Now, so suppose if this is the metastable ion, then it will show the peak at non-integer value. So peak position, that can be determined by using this one. So peak position for this metastable ion, suppose this is M2, this is suppose, and this is M2 plus, and this is suppose M3 plus, and this is suppose M1 plus. So for this term, position can be determined as, how can we determine the position? So this is formed from here. This is our parent ion. So 108 square divided by your 123. So so this will give you the position of metastable ion, and suppose this is coming at 94.6 something. So this is coming. In the same way, if we find the peak metastable position or the position of this metastable ion, then due to this metastable ion, then this is 80 multiplied by 80 divided by, is formed from this, so 108. So this will also give you the non-integer mass M by Z value. So like this. So this is about the metastable peak. And next type of peak that I should discuss is the isotopic peak. So what I told, these peaks, small peaks, which are, you can see like this in the neighbor of this peak. In the same way, this small peak in the neighbor of this peak, another peak, this is a neighbor, this is a peak in neighbor of this peak, and having, you can see the mass M by Z value 1 mass unit higher. This is 1 mass unit higher, this has 1 mass unit higher, this has 2 mass unit higher, and so on. So next type of peak, that is important peak, is the isotopic peak. Now fourth one is the isotopic peak. So this isotopic peak, it has, suppose molecular ion peak is, this is our molecular ion peak. Then isotopic peak will have mass number greater than 1 by this, suppose M plus 1, this would be the isotopic peak. Another M plus 2 may be the isotopic peak, M plus 4 may be the isotopic peak, 4 unit higher, 2 unit higher, M plus 6 unit higher, and so on. So these isotopic peaks are due to the presence of isotope of the atom. So if any compound is containing the carbon, then its isotope would also be present in that sample. So carbon containing sample, that is carbon 12, it must contain some small amount of isotope, that is carbon 13 would also be present. In the same way, carbon 14 will also be present, but its relative abundance is very less in comparison to the carbon 12. Now suppose we know that if chlorine is present, and chlorine having the mass number 35.5, then its isotope will also be present, that is chlorine 37 will also be present. In the same way, bromine is present, then bromine is also having the isotope, that is bromine 79 and then bromine 81. So 2 mass unit higher isotopes. So due to this, because if any compound is containing carbon 12, then it must contain very less amount of carbon 13 also. If any compound is containing chlorine, then it must contain its chlorine isotope, that is chlorine 37, and so on. So that due to that, if peak appears due to carbon 12, then the peak will also appear due to the carbon 13, which is 1 mass unit higher. So that's why. So these are the various isotopic peaks. For example, for C12, for carbon, we may have, that is M peak and M plus 1 peak. M plus 1 peak will also appear. because this is due to the carbon 12 and this is due to the carbon 13 isotope. And M plus 2 peak, suppose, due to carbon 14, but its intensity will be negligible or very small in comparison to this one, because its relative abundance is very less. So suppose if this is out of 100, so the relative abundance of this carbon 12 is 98.9, and this has 1.1%, and this has suppose 0.015%, like this. In the same way, if suppose if we have chlorine, then this chlorine, it will show M plus M peak and M plus 2 peak, and this M peak is due to chlorine 35 and this is due to chlorine 37. And if you see the relative abundance of these two isotopes in a chlorine, then this chlorine is 75%, around 75.5% is this, and 24.5% is chlorine 37. So this is the approximate ratio of this. In the same way, if we have a bromine, then bromine, if it is present, then it will, if bromine is present in a molecule, then molecule will show the isotopic peak. And this isotopic peak, one is the M peak and that would be the M plus 2 peak. So bromine is having the mass unit, that is 79, and its isotope is containing the mass, that is 81, is this one. And if you see the relative abundance for this, then it has around 49.5%, this one, and it is having the relative abundance of again rest of the that is 1:1 ratio is present. So 1:1 ratio, that is 51.5, like this. Okay, so this would be, I think this is for 51.5, and this is, so this is 50 to around 50%, you can say 50% this, 50% this, that is 1:1 ratio is present. And here if you will see, then this is 3:1 ratio. This is 3:1 ratio of these two isotopes is present. Okay. So the intensity of this isotopic peak, it depends upon the relative abundance of its isotope. Now, for example, suppose if I have C6H6, that is benzene, if I have benzene C6H6 is there, then this carbon will contain the some isotope, carbon 12 and carbon 13. Then what would be the intensity of, if you are asked to find the intensity of M and M plus 1 peak, what would be the intensity of N and M plus 1 peak? And how we can find the intensity? And suppose I may take the intensity, because intensity is taken of these two, M and N plus 1 peak, this is the relative. So if it is 100, then how much this one? So suppose if I take, if 100 is the relative abundance of, or intensity of, suppose M peak is, say intensity M peak is, say, 100. It is 100%. Then what would be the intensity of M plus 1 peak? So intensity of M plus 1 peak is calculated. Suppose if I have C6H6, then what I told you, for M plus 1 peak, so I have to find the intensity of M plus 1 peak. For M plus 1 peak, C6H6 the means for carbon 13, M plus 1 means for carbon 13. So carbon 13 is say it is 1.1%. How much carbon 13 is present? 1.1%. So 6 carbon is present. So its abundance would be how much? 6 multiplied by 1.1. Okay. So in the same way, hydrogen may also have the isotope. Hydrogen may also have the isotope, but it's like deuterium, tritium. But its relative abundance is very negligible in comparison to the simple hydrogen. So deuterium, tritium has a negligible relative abundance in comparison to the hydrogen, and so the relative abundance due to hydrogen may be neglected. So main thing is due to the carbon. So this is equal to 6.6. So what would be the intensity of this two? So m upon m plus 1 ratio, intensity ratio, this would be, this is I have taken as 100, and due to this 6 carbon, the relative abundance is 1.1 multiplied by 6. So this is 6.6. So this comes out to be around 15, suppose 15 multiplied by. So if intensity of this m peak is 100, then intensity of your m plus 1 will be 6.6 only. So it means your spectra, suppose this is the molecular ion peak. If this is the molecular ion peak, then suppose this is 100, then one of the peak will appear like this, and its intensity is around, this is suppose 6.6, only 6.6, this is 100, this is 6.6, like this. Now in the same way, suppose if I have, so this is about m plus 1 peak. Now we can also find the intensity of m plus 2 peak. Suppose you are asked to find the intensity of m plus 2 peak. What would be the intensity of n plus 2 peak? Then the intensity of m plus 2 peak is given by the formula intensity of m plus 2 peak is given by the formula 0.006 multiplied by n square. So whereas this n is the number of carbon atoms, this n is the number of carbon atom in the molecule. Okay, now for this C6 at 6, what would be the intensity of m plus 2 peak? So it can be determined by this formula. So m plus 2 peak, if you are asked to find the m plus 2 peak, intensity of m plus 2 peak, so this is equal to how much? 6 carbons are present. So 0.006 multiplied by 6 square. So this is equal to 0.006 multiplied by 36. This is this thing, and it would be around this is 0.216. That would be 0.216. So this is very less. This is very less in comparison to this is 6.6. This is 0.216. So intensity ratio like this we can find. Suppose if we have the intensity of m peak and m plus 1 peak, which we also see from this spectrum. From a spectrum we can find we can compare the intensity of m peak and this m plus 1 peak. So from these two intensity, m and m plus 1 peak, we can also find the number of carbon atom in any unknown molecule. And this is very important information that we may have. So from this intensity, from the intensity of m and m plus 1 peak, we can find the number of carbon atom. And the formula for this is number of carbon atom. This is equal to intensity of m plus 1 peak divided by 0.011 multiplied by intensity of m peak. Okay, so this is very important formula. And suppose by using this formula, if you want to find the number of carbon atoms, say we know from spectrum what we have, so we see that intensity of m plus 1 peak, suppose This is 5.5%. Is the intensity of M plus 1 peak. And intensity of M peak is say 100. This is 100. These two intensities are given. Then what would be the number of carbon atom in a molecule? So number of carbon atom, this is equal to, according to this formula, this is equal to 5.5 divided by 0.011 multiplied by 100. So this is equal to how much carbon is present? So 5.5, this is equal to 1.1. So 5.5 divided by 1.1, this is equal to 5. So number of carbon atom is 5. So we can find it from this isotopic peak. We may get very important information about our unknown compound. Now, in my next lecture, I will discuss about some more about the isotopic peak or this isotopic clusters. Thank you.